Hey guys, I'm Jed. Welcome back to my LeetCode Review One Take vlog on the 909th problem, Snakes and Ladders. Before we start, let's get a snapshot of the example 1 here to understand this problem easily. Okay, we are given an n times n integer matrix board where the cells are labeled from 1 to n squared, where n is 6 here in example 1. Starting from the bottom left on the board, which is square 1 here, and alternating direction each row. For example, 1, 2, 3, 4, 5, 6 is in this direction, 7, 8, 9, 10, 11, and 12 is in the reverse direction. We start on square 1 of the board. In each move, we start from square current, and we need to do the following. First, we choose a destination square next with a label in the range. Current plus 1 or the minimum between current plus 6 and n squared, which means we can only move from 1 step to 6 steps. And if next has a snake or ladder, we must move to the destination of that snake or ladder. Otherwise, we move to the next. For example, if we move from 1 to 2, then we're going to move to the 15 because we have taken the ladder. Or if we move from 15 to 17, then we take the snake. So we'll fall back to 13. And the game ends when we reach the square, n squared, which means we need to reach 36 in the example 1 here. A board square on row R and column C has a snake or ladder if board of R, C is not equal to -1. The destination of that snake or ladder is board of R and C. Square 1 and n squared are now the starting points of any snake or ladder. Note that we only take a snake or ladder at most once per dice roll. If the destination to our snake or ladder is the start of another snake or ladder, we do not follow the subsequent snake or ladder. Finally, we'll return the least number of dice rolls required to reach the square n squared. If it is not possible to reach the square, we'll return -1. So for example 1 here, we start at a square 1 and we decide to move to square 2 and must take the ladder to square 15. Then we decide to move to the square 17 and must take the snake to square 13. Then we decide to move to square 14 and take the ladder to square 35. And here comes the final step. We just move 1 step forward to the 36th square and we end this game. So the minimum number of moves to reach to the last square is 4. So our output is 4. Okay, let's get started to the intuition and the idea of this problem. When we look at this problem, we can regard it as a shortest path problem in a graph. Each cell or each square on the board is a node, and from each node we can move to at most 6 other nodes, simulating a dice roll. If there's a snake or ladder, we must take it. And we have 2 different solutions. First, we can use breadth first search with Q, the classic approach for shortest path problems, or Dijkstra's algorithm. Now, let's start with the breadth first search with Q method here. We'll use breadth first search to find the shortest path from cell 1 to cell n squared. We'll maintain a queue of positions to explore and visit state to avoid cycles. For each position, we'll try all possible dice rolls 1, 2, 3, 4, 5, 6. And we'll use the breadth-first search to find the minimum number of moves. Inside code, we start by determining the size of the board. Let's say integer n gets board.length. Then we'll use a queue for breadth-first search to find the shortest path. Queue of, let's say, integer called q gets new linked list. Linked list. Then we need to check which cells we've already visited to avoid cycles. So we'll declare a Boolean array. Called visited gets new Boolean. And the size of the Boolean array is n times n plus 1. And let's start the breadth-first search from cell 1, which is the starting point. And code is q.offer of 1 and visited of 1 gets true. Then we need to initialize the number of moves to 0. Let's say integer moves started at 0. Then we need to create a while loop to begin the breadth-first search traversal. Let's say while not logical symbol q dot is empty. Inside the while loop, for each iteration and each level of breadth-first search, we need to process all cells at the current distance. So the code is, let's say integer size gets q.size. Then we need to process all the cells at the current distance. So we'll create another inner for loop for integer I started at 0. When I is less than size, we'll increment I after each iteration. Inside inner for loop, first we need to get the current cell. Let's say integer current gets q.poll. Poll. Next, if we reach the destination, we need to return the number of moves. So we can have an if check if current equals n times n, which means we have reached the final square. So we'll return the minimum moves. Or we'll try all possible dice rolls. So we'll create another inner for loop, let's say for integer of j. For integer j, starting at 1, j is less than or big or equal to 6. We'll increment j after each iteration. Inside this for loop, first we'll calculate the next position of the dice roll. Let's say integer next gets current plus J. If we've gone beyond the board, we need to skip the row. So we have a valid check. If next is bigger than n times n, which means it's an invalid move. So we'll skip the row. Continue. Then we'll convert the cell number to board coordinates. Let's say integer array called coordinates. Coordinates get coordinates of next and n, and we'll implement the get coordinates method later. Then integer row gets coordinate of 0, and integer column gets coordinate of 1. Then we'll check if there's a snake or ladder at this position. If board of row column is not equal to -1. If so, we must move to the destination of the snake or ladder. So the code is next gets board of row column. After that, if we haven't visited this cell yet, we need to add it into the queue. And the code is if not visited of next. If so, we'll assign this value to true. Visited of next gets true. And we need to add it into the queue. Queue and offer of next. And after that, we'll increment the number of moves for this level of breadth first search. Increment moves. And out of the while loop, if we can't reach the destination, we need to return -1. Okay, that's all the code for this method. Then we need to implement the helper method we mentioned before, which is get coordinates. We need this helper method to convert cell numbers to board coordinates. Let's say private integer array get coordinates of integer cell and integer n. First, we'll adjust the cell number to 0 index. So we'll subtract 1 from the cell. Cell gets cell -1. Then we calculate the row and column in a normal grid. Integer row gets n -1 minus cell divided by n. Integer column gets cell modulo n. Finally, we'll adjust the column for each rows to handle the handle the style. If, let's say, n minus 1 minus row modulo 2 equals 1. If so, column gets n minus 1 minus column. Finally, we'll return the coordinates as an array of row and column. Return new integer array with row and column. Alright, that's all of the code. Let's submit our code and check if our solution passed all the test cases. Oops, there is something wrong here. Let's resubmit again. Coordinates. Class solution cannot find a symbol. It's on line 24. Yes, this is my problem. The correct name is coordinates. I forgot the S symbol, letters. Yes, our code got accepted. Now, let's analyze the time and space complexity. For the time complexity, first, we have n squared cells. And for each cell is visited at most once due to our visited array. And for every cell, we consider up to 6 next moves, which is also big O of 1. And the coordinate conversion is also big O of 1. So the overall time complexity is big O of n squared. Next, for the space complexity, first, the Q can grow up to big O of n squared. In the worst case, because we could add all the nodes into the Q. And the visited array is of the size of n squared plus 1. N squared plus 1. And their coordinate conversion and other variables use big O of 1 space. So overall, the space complexity, it is also big O of n squared. And this is the end of my LeetCode review vlog on this problem. And I highly recommend you guys to visit my online GitHub page here, which contains all the problem description. Let's see the problem here. You can see all the problem descriptions, intuition and main ideas, and different solutions with very detailed comments, and final time and space complexity analysis. You could also visit my GitHub repository here, which contains all the codes and notes to build this online GitHub page. And I'll put those 2 links on my YouTube description below. And thank you guys for watching, and I'll see you next time. Bye bye.